Hello everyone, I'm Raufun Nahar from Shizuoka University, Japan. I will discuss about effect of data augmentation on DNN-based VAD for automatic speech recognition in noisy environment. In this presentation, I will cover following topics. Now, moving on to the background and motivation. In case of an ASR system, we train an acoustic model using clean features extracted from clean speech using ideal segmentation information provided by the data corpus. Then, when using the ASR system for recognizing unsegmented long recording, we need to first separate the speech segments using a voice activity detector. But extracted features using estimated segments cause mismatch. This mismatch grows larger if there is distortion and noise present in this test data environment due to more inaccurate segmentation. Therefore, we carried out this research to deal with segmentation problems in such situation. I have mentioned VAD before, but what is a voice activity detector? A voice activity detector or a VAD is a system or operating unit that can detect a segment of recording as speech or non-speech.
VADs can be loosely divided in two groups, conventional and modern VADs. Conventional VADs are rule-based. They are difficult to optimize when used with modern ASR systems. On the other hand, modern VADs are DNN-based classifiers. They have already outperformed rule-based methods. They are easy to optimize along with modern ASR systems due to their DNN-based nature.
As stated in the previous slide, DNN-based methods of VAD performs better, but the performance is often evaluated for clean speech. If the data contains distortion and noise, such as telephone speech, then they need special attention while performing VAD. There are larger DNN-based models to address this problem. Those include denoising component as well as classifier components together. But larger models demand larger computational cost. We also try to overcome data deficiency problem in target domain by creating augmented training dataset using minimum amount of simulated distorted noisy data. Next, I am going to discuss the data augmentation techniques we have observed in this research. These data augmentation techniques and observation about them are going to be the main focus of this research. Before jumping into data augmentation procedures, I would like to mention the conditions of clean and augmented data lightly, as the minimal set of clean data that also take part in data augmentation is a subset of corpus of spontaneous Japanese CSJ training data, which are long recordings of monologue speech. Though using a larger dataset is possible and encouraged in this research, I will discuss how minimal data affects the segmentation and ASR performance. The augmented data is simulated using G712 filter and a subset of JADA noise database to include distorted and noisy environment. Though the original segment level using interposal unit provided by CSJ transcription for long recordings are available, we have prepared target level using forced alignment derived from ASR system. Since the original label may include short pause in speech segments and we are using a DNN-based VAD that estimates speech or non-speech frame by frame, therefore we have created frame level target label assuming that it will give better performance.
Now, I will discuss the data augmentation approaches. Those are proposed in this research. First, I will describe how the training data is augmented using clean data only. We will call this dataset DNN Clean 24 hours, again DNN Clean, that uses minimal clean data to train DNN. In the case of DNN Clean 24 hours, we have added 2 times larger additional data to DNN Clean dataset and tripled it in size. Along with the length of data, the number of speakers grows from 24 to 100. It implies increasing variations of speakers in clean data. Another data augmentation approach is called DNN-Multi. The DNN-Multi uses DNN clean dataset of minimal clean data as seed. Filtered and noisy data are simulated using this clean dataset to deal with noise and distortion of telephone environment. This implies increasing variations of environments for each speakers as the number of speakers remains the same. There is one more approach of data augmentation observed in this work. This approach will be called DNN Multi 24 hours. Since it uses variation of clean data of 24 hours described as DNN Clean 24 hours previously, here we have additional 16 hours of clean data other than DNN Clean dataset. We divide them in two sections of similar length and apply filter on them. This produces finally add filtered noise to one of the sections only. This produces an augmented dataset of 24 hours in length, but the number of speakers grows from 24 to 100, meaning increasing type of environment and number of speakers. That's all for data augmentation techniques.
To summarize the baselines and DNN-based approaches, we compared the performance of 3 feature-based baseline VAD methods as opposed to 5 DNN-based approaches. To evaluate effect of segmentation on ASR performance, we compare 4 DNN-based VAD methods as opposed to ideal segmentation provided by corpus. The baseline methods will be introduced in next slides. Among the DNN-based methods, there is DNN multi MFCC, except that all the other DNN approaches are based on Mel-Finterbank features. We only compared the VAD performance of DNN multi MFCC as opposed to DNN multi F-bank to determine the most effective feature. We evaluate VAD models itself for VAD task and the effect of segmentation using DNN-based VAD for ASR task. To evaluate VAD task, we have used simulated evaluation set of SenseRec 1C corpus. To evaluate the effect of segmentation on the performance of ASR task, we have used eval1 test dataset of CSJ and its telephone versions eval1 land and eval1 mobile. eval1 land and eval1 mobile is recording using landline telephone and mobile telephone respectively. They contain distortion caused by telephone line or network as well as surrounding noise. Then I will describe the baseline methods. As previously mentioned, we have compared performance of 3 baseline VAD methods. The first one is SenseRec 1C baseline, and the second one is add-in tool by Julius, and the third one is FVAD wave using libVAD of WebRTC native code package. All of them are rule-based or statistical-based methods. After baseline methods, now I am going to describe the structure and configuration of DNN-based VAD. The DNN-based VAD we have used uses a very simple structured deep neural network. The DNN takes feature vector as input and learns to classify using backpropagation method. In this research, we have used Mel-Filterbank features of 40 dimensions, pitch of 3 dimension along with delta 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 features. We used 5 frames before and after each frame as context in the input layer. This DNN has 3 hidden layers with 512 hidden units in each hidden layer.
Now, I would like to lightly describe the DNN acoustic model that is used as ASR system in this research. The DNN-AM is trained using 948 clean recordings, which is a subset of CSJ training dataset. It contains 286 hours of recordings in total. This model has a simple DNN structure similar to the VAD model.
Now, moving to the experiments.
In this slide, I will explain utterance level performance of VAD methods. Here, utterance level decisions are made from frame level decisions. First, performance of baseline methods. Among three baseline methods tested on SenseRec 1C test set, simulated test data, SenseRec 1C baseline performs the best. The other two methods do not perform well in presence of noise. Then we compare the performances of DNN VADs for clean training data. Between two DNN methods, increasing clean data increases overall performance since it works well on clean data and noisy data with high SNR values. Now, if we look at the performance of other three methods, we notice that between DNN multi-MFCC and DNN multi-FBank, using FBank features helps DNN to perform better. Finally, comparing DNN multi and DNN multi 24 hours accuracy graphs suggest that DNN multi has better performance. It means when augmenting training data using variation of environment for each speaker produces better performance than increasing number of speakers for a certain environment when performing segmentation. Now it is time to explain the effect of segmentation methods on ASR performance. We perform evaluation using variants of eval1 test dataset of CSJ as described earlier. First, I will describe the recognition performance using word error rate percentage for ideal segmentation. Performance of clean test data is the best among the three. Second best is landline recording and the worst is for mobile, which contains the most distortion. This performance relationship is visible for other comparing methods too. Then the performance of VAD is VAD trained with variants of clean data. If we increase the size of clean data, then the performance of eval1 improves the most. Even there is relative improvement in performance for telephone speeches. So we can say that increasing clean data helps the VAD to perform better segmentation. Finally, we compared the training data augmentation methods for DNN multi and DNN multi 24 hours with others. Looking at the performance of DNN multi, we can conclude that including noisy data with variants of environments to the training data helps improve segmentation performance, resulting in overall performance improvement for ASR task.
Finally, it is time to conclude the research. In this research, we focused on DNN as a segmentation tool in different noisy environments. We also compared the effect of segmentation on ASR performance. The conclusion is that in both cases, what type of variation is used when preparing training data affects the performance strongly. Using multi-condition training data created from same clean data performs better than using multi-condition data created from different clean sources. In near future, we plan to perform adaptation of acoustic model to increase performance on real-world noisy speech. Data augmentation for training adaptation can be performed. To do so, we can use a transformer model created using pairs of clean and noisy data accordingly to create more noisy data. We also plan to investigate the effect of increased clean training data by adding as much as clean data as possible. More variation in speaker as well as variation of environment for each speaker is assumed to yield best performance is in segmentation. Thank you for listening. If there is any question or comment, please leave them in the comment box.